Hello, you are welcome to the second part of this tutorial. In this second part, I will be running and showing you the simulation demonstration of the design. What we need to do now is pick up the required active components from the Proteus library. We need an AC source, which is an alternator, a motor, a fan and a motor to determine which works best between the motor and the fan to represent our ceiling fan, a 1-pole 2-terminal switch, a resistor, and a lamp. That's all we need. We start by placing them in the design. We place our lamp for our lighting points, the DC fan to represent our ceiling fan, the alternator to represent our incoming consumer's utility cables, and the switch. We need this resistor to form our regulator. We also need to get a fuse. We place 2 active fuses for our switchgear. Click on Terminal Mode to select the default terminal for our wiring. Connect the wire from the default terminals to the component terminals. Right-click on the wire, select Edit Wire Style, and then adjust the wire's color and size as desired. After linking up the default terminals to the components, right-click on this line, copy it, and paste it. Use it to link from the existing line to the wires, editing the color of the line to match the wire color. We properly arrange the active fuses. Then connect a default terminal to their incoming and outgoing terminals. After editing the wire style, copy the line and link the wires to the input and output lines of the gear switch accordingly. Double-click on the alternator and change the voltage value to 240 volts and the frequency to 50 Hz. You can double-click on any default terminal and give it a specific label or name. Default terminals linking to each other must have the same label or name, and their labels must have the same size, color, and other properties. Otherwise, they will not work. We then give the default terminals at the incoming of the switchgear the same name as the ones entering the meter, according to their color. We give different labels to the default terminals at the output terminals of the gear switch. With the connections already done, you should understand what I am doing and be able to follow along. Let's move faster. Here is the complete wiring connection for the design. Lamp 1 and lamp 2 are already connected, and the fan is also connected. I decided to use an active DC motor instead of an active DC fan because it works more perfectly. I later changed the resistor to an inductor for my active fan regulator, knowing that a fan regulator is made up of coils. This fan regulator has 3 speed levels: coil 1, coil 2, and coil 3. I used this jumper to represent the off state of the fan. This is the fan branch. You can see the connection through to the fan. Here is the mains, which supplies power from the DB. It passes through this pipe layout to the switch, looping to the fan regulator switch. This is the same mains, connecting this switch. This active switch represents the picture switch. So, the mains wire runs through to this active switch. You can see it here. Here is the light branch wire that supplies power to the lamps, lamp 1 and lamp 2. We assume the rating of our gear switch to be 100 amps. After connecting these active fuses to represent the gear switch, right-click on them, go to Edit Properties, and change the rating to 100 amps. From the gear switch, power is fed to the DB. This is the DB, the distribution board. We have 10 amp and 15 amp miniature circuit breakers. I am only showing the fan and lighting point simulation demonstration. This red wire feeds the fan and lighting points. I used an active fuse to represent this miniature circuit breaker. Right-click on it, go to Edit Properties, and change the rating to 10 amps. It will carry our lamps and fan. Adjust the ratings of lamp 1, lamp 2, and the fan to match the fuse rating. After increasing your voltage, also increase the resistance higher than the voltage. Right-click, go to Edit Properties. Change the nominal voltage to 120 and change the resistance to 240 to reduce the current the lamp will draw. Do the same for the other lamp and fan. If the sum of all load currents exceeds the fuse rating, the fuse will blow. Let's do the demonstration. It is now running. Everything is off, as we can see. The 1-gang switch controls the 2 lamps. When we turn the lamps on, they light up. Let's turn them off. Let's keep them on. Coming to the fan regulator switch, it is not rotating because it is on the jumper, the off state of the fan. When I rotate it, the fan starts rotating but at the lowest speed. Increasing the speed shows a faster rotation. You can see it. This demonstrates how it works. Let me return it to the off state. To form the regulator, adjust the inductor's parameters to get different speed levels. Let me show how the fuse representing the miniature circuit breaker can blow when overloaded. Reduce the lamp resistance to 24 to increase the current. Watch closely to see the spark. I hope you saw the flash of light. The fuse wire inside the fuse is broken because the load current is greater than its rating. In physical design, accurately calculate the loads that will enter a miniature circuit breaker before choosing one. The loads determine the particular rating of the miniature circuit breaker to be used. I believe you learned something today. Thanks for watching. Do well to subscribe to my YouTube channel for more updates.